So welcome everybody, my name is Vadim Bulitko. I'm the Department of Computing Science at the University of Alberta. So flow is meta control. It's a joint work with my master's student, Story Mary's daughter, and my postdoc, Matt Brockman. Okay, so flow, most famously known as the work of Csikszentmihalyi, pictured on the slide, a Hungarian-American professor. And the idea was that when the task has certain properties, then the agent, in this case human, he was a psychologist with humans, enters certain states. So the conditions that are required are clearly defined goals and measured progress in the task. You have immediate feedback available to the agent. Skills match the complexity. What's important is that the match is dynamic. So as human skills go up, so should the complexity to keep them in the same flow. So the diagram actually shown here, this flow channel or tunnel as it's known, is taken from a book on game development. And game developers, video game developers, have been talking about this for a number of years. In fact, there is a conjecture that the reason video games is so attractive, sometimes even addictive, is that they manage to get the person in a state of flow and keep them there. Okay. And they do this by carefully designing game levels and progression of difficulty in the game so that as you become better at the game, so do the levels increase. So maybe if you're playing Doom, right, initially the levels are simpler and they become more complex, and the topology changes and so on. So when you enter the state of flow as a human, Csikszentmihalyi postulated that that's actually a primary source of enjoyment and happiness in one's life, or one of the primary sources. So there's several consequences of entering that state. One is that you have a full concentration on the task. You also have this order in consciousness, which he postulated was inherently or intrinsically rewarding. So humans try to reduce entropy in their mind. That was his convention. It's also intrinsically rewarding, so it doesn't matter how much the task pays or whether it delivers food or whatever other gratification, just being in a state of flow feels good. And you also have loss of reflective self-consciousness. You're no longer going to step out of the moment, you're in the zone, you don't think of yourself doing it. And he also postulated that optimal performance is achieved. In fact, one of his books was called Flow is Towards Optimal Performance, something of that like. So I'm going to focus on the particular two conditions here, that skills should match complexity and that matches dynamic. And that's the part which I'm going to transfer from psychology to AI and argue that it's maybe useful. Okay. So there have been a number of projects trying to explore this. So some of them were in psychology, and in fact both of them were psychology. So originally, Csikszentmihalyi himself used pagers at the time to interrupt somebody's daily routine, and they had to, as soon as the pager would buzz, they would pull out, produce a form, and they had to fill it out, trying to figure out how they were feeling, whether in flow or not. Later studies used functional magnetic resonance imaging, trying basically having people play video games while in the fMRI machine, and then measuring what happens to their brain. And then if you distract them from the game while they're playing, you can see what changes in the brain, because presumably they're exiting the state of flow. Right? So there are some issues here. One is that all these pagers and so on, they interrupt the experience. And at the moment the flow is interrupted, you may not be no longer in a state of flow, and so it's not clear how much you still remember and how much you can fill out. The fMRI studies actually do not have any conclusive results of flow to date, as far as I've seen. Another problem, I'll go back for a sec, is that there's no computational model of flow accepted. Right? It's at a qualitative level. When this happens, but how much, right? How much of this needs to happen and how much of the flow are you going to receive? And the final question is, can flow be beneficial to our agents? So I'm going to argue that yes, it can be in certain ways. Okay, so which ways? So why do we want to study flow in AI? So I think there are several reasons it may be of interest. One is that if you consider a task of transfer learning in AI, so this is very common. So if you have certain tasks where learning an easier task can benefit, can be helpful for learning a harder task. And for humans, it's very common. So if you're learning to downhill ski, you're probably not going to start with like diamond run. You're going to start with some bunny hill and then progress and so on. And there have been quite a bit of work in AI planning, what people here refer to as narrow AI, trying to order the tasks in planning so that whatever you learn in a domain-independent terms in a simpler format will transfer learn to the next. So the sequencing is often done in AI planning. The sequencing of these domains is done by an external coach, right? A human who's going to go this domain first and that domain. So I'm arguing that the sequencing can be done by using flow. So that's the first application. The second application is that, as I mentioned, video games try to keep the player in the flow, but they do this by basically leveraging the task of video game developers who carefully design the game levels. Can we do this adaptively? Right? Not all players are the same. Not all players learn the same speed. That could be also transferred outside of games. So what's shown here is a person frustrated with something. Maybe she's checking some dating site, or maybe she's doing some online learning. Right? So now everybody is very excited about MOOCs, massively online open courses. And they collect a lot of telemetry, but not many of them actually use it to change the delivery of the material ordering in a particularly sophisticated way. Okay. And then my own area of research is interactive storytelling, where we're trying to have game mastering to be done by artificial intelligence. Okay. So 2 years ago, I presented work at Pat Langley's conference on cognitive systems, the first annual one that he organized in Palo Alto in December 2012. And the idea was that if you have a reinforcement learning agent which is receiving rewards, you can mix in another signal, the flow reward signal, which arises when your skills, or the agent skills, match the complexity of the task. And it worked pretty well, but it was very limited at the time, and it required reinforcement learning underneath so that you can do basically reward shaping by mixing in another signal. The current work that I'm talking about here gets rid of that requirement. So I'm no longer requiring that underlying agent is in any way limited to our paradigm. It could be in any policy, any control policy, and what I do now, I have an external policy which decides which task to pick next. To do that, I'm going to split the entire world into a series of tasks or levels, right? So video games provide a good analogy. You often have levels, right? You're clearing this stage and now onto this stage. But it can be anything. It could be a MOOC. You're progressing from ordinary or differential equations to partial derivatives, differential equation to partial derivatives, and so on. Okay? And the way we're going to measure performance is that the agent needs to reliably achieve the highest level as quickly as possible. Again, so if you think about skiing, you want to progress perhaps to the black diamond without killing yourself, right? Reliably to do that and survive. So there's some details in the paper. I was told that the papers will eventually be available on the website of the conference, but it's also on my own website already, so you can look at it there. So this is a screenshot from an old game called Angband, which is a text-based dungeon crawler. And just like in many role-playing games, you have skills describing, variables which describe the skills of the character. So in this particular case, you have the armor class of 10, and you have hit points of 20, and dexterity of 8. But any game, let's say you're playing some Shadowrun Returns or something like that, you will have certain points which you can describe the abilities of the character in. So, an AI policy in Angband, there's an AI policy hand-coded. It's a big, messy code. Hopefully the author is not here of the code. But it's quite large and it's complex. So what it's doing is deciding how quickly to progress through the dungeon levels. And it's all hand-coded. So what I'm suggesting is that instead of hand-coding that, we use a flow maximizing policy. We try to match the vector of features to the vector describing the complexity of a particular dungeon level, And the flow, the amount of flow, is basically the divergence, inversely proportional to the divergence of those two. So the closer your skills are to the required, to the complexity of the levels, the more you are in the flow. That's, in a nutshell, that's all there is. So now you have a meta control policy, which is, okay, I'm at the level 5. I can go back up to level 4, which is easier, or I can go down into the dungeon to level 6, which is tougher. Where I can just stay where I am at level 5? What should I do? Easy. You compute flow for level 4, level 5, level 6, and then take argmax, whichever level gets you the highest estimated flow. Okay. So in this particular case, I'm using flow as 1 over the Euclidean distance between two vectors. One of them the agent abilities, and the other one is the level complexity. Okay. So it's a simple approach. I'm illustrating it with a primitive formalization, but that's just to show that presumably it's broad enough to be applied to a variety of tasks. And what you can do to evaluate this, you can see how quickly you get into a certain level reliably. And by the way we can quantify reliability is that if you actually die in the process of your progression through scheme levels, you forfeit all the rewards you collected. Right? So you want to be fast enough, but not faster than necessary. Okay. And it turns out, again, in terms of time, I'll skip that, but this top curve is a flow control agent. For any terminal level that we pick in this unbanked progression of levels, the flow control agent is more reliably getting more out of it, more return and more reward. Right? And this is a standard built-in control policy. Okay. So in the future work, I would like to look at how to define complexity. So I didn't mention how I define complexity so far. The way I do now is by societal learning. In other words, my agent observes a whole bunch of other agents who try to descend through this unbound levels at different speeds, and it looks which ones made it to the end. Right? So the ones which made it, those presumably had sufficient skills. So out of those skills, I can take the minimum, let's say per component, and that becomes the minimal required skills to survive. That's it. Okay. But you can also look at the curiosity-driven learning, such as TD aerodynamics. You can take derivative of the temporal difference error and see how quickly it's going down. If it's not going down quickly enough, perhaps you're in over your head, and you're learning enough. You can look at state representation and even evolution. I mean, some argue that perhaps this complexity function was given to the agent simply via generations of evolution. I'm currently looking at real-time heuristic search, which is depicted here. Okay. It's a convenient to visualize domain. And what's also interesting is the profiles, complexity profiles could be multi-dimensional. So for instance, maybe if you're an animal in Africa, to survive predators, you can either fly, but not run very quickly, or you can be a ground animal, run very quickly, but not being able to fly. So if you just take minimum of both components, the flying skill and the running skill, that's bad, because you're going to say, okay, well, I've seen animals which survived, couldn't run, and I've seen animals which survived, which couldn't fly. Therefore, to survive, you don't need to fly or to run. Of course, the reality is you need to have at least one of them. Okay. So we're currently experimenting with that simply by doing clustering. Okay. There's also a question how you describe skills, and what are the features they use to describe skills. We have been working on auto-encoding networks to select that. And so in summary, if you know something about yourself, by you I mean the AI, AGI, if you will, agents, and if you know something about the abilities required to achieve things, then you can try to, and higher levels are desirable, or deeper levels, or so on. And being underqualified is dangerous. If all of these conditions come together, then perhaps it makes sense to choose whatever area of space, level, task, according to your skills. So a very simple idea, but perhaps somehow relates to these grand goals of order and consciousness and so on, or perhaps not. Thank you.